Hello everyone, this is a continuation on evaluating limits algebraically, but using some new strategies. So in the previous video, we talked about how if you're not given a table, if you're not given a graph, if you can't use direct substitution because you get undefined, then you can factor, right? Here I have an example of another problem where we're going to be evaluating the limit algebraically. However, factoring isn't really helping. And I can't use direct substitution because if I were to plug in 0 for x, again, I end up with undefined because I have a 0 in the denominator. So I can't really use direct substitution, and factoring just isn't an option either. So what we have to do for this problem is use a series of complex fractions where we are dividing a fraction by a fraction. And so I know that I can only use a complex fraction if I'm dividing a single fraction by a single fraction, right? Then I can use the hamburger method, or you can multiply by the reciprocal, but you can only have one fraction divided by one fraction. In this example, I have two fractions divided by what would be a whole number. So I'm going to manipulate this a little bit so that I have one fraction on the top and one fraction on the bottom. Okay, so the first thing I'm going to do is try to combine my numerators so that I end up with only one fraction. So in this case, I can only subtract. Again, I'm subtracting fractions here. If you recall, we can only subtract fractions that have the same denominator. So if I wanted to subtract 4/5 minus 3/5, I can do so because I have the same denominator of 5, right? So in this case, if I want to subtract these two fractions, they need to have the same denominator. And so a huge mistake that I see some students make is that, okay, they have the 2 in common and they're just missing the x. Nope, that's illegal. Math jail. You can't do this. We can only multiply values to my fractions on the top and the bottom. No addition or subtraction. Okay, so I can't just add x like that. Instead, what we would have to do is I can multiply by the alternate denominators. So I'm multiplying by 2 plus x on the right, and then I can multiply by 2 on the left, okay? And in doing so, I'm going to look a little bit like 2 over 2 plus x, and after a little bit of simplification, I can see that I get the same denominator, and so I can combine those denominators and you have to be careful here because when we subtract the numerators, this subtraction is being applied to the entire expression. So that does mean that we are going to need to distribute the negative here, okay? So after distributing, we get 2 minus x, and I end up with negative x over 4 plus 2x, okay? Now, this is only the numerator. All of the math that we just did was only to combine the fractions in the numerator. I still haven't even touched the denominator. So I'm going to bring down my denominator of x, okay? So this still needs to be divided by x. And so remember that I said that we can only divide fractions by fractions. So what couple options you can do here. You can either try to divide by x over 1, make it into a fraction, and now you can do the hamburger method. Or you can multiply by the reciprocal. So if you've taken my class before, you know that I love to use the hamburger method because it's just real simple. But if you've never used the hamburger method, it's where you multiply like the buns of the hamburger, and that would be your new numerator. And then you multiply like the insides of the hamburger. Oops. There we go. And that becomes your denominator. I don't know why it's called the hamburger method, but that's what it's called. Okay. All right. That is my final expression after I have taken into consideration my denominator. Now, again, you could use a hamburger method like I just did, or you could have multiplied by the reciprocal, and I'm going to show you that you get the exact same thing, and you can use whatever method makes your heart happy. So if I had negative x over 4 plus 2x, and I'm dividing by x over 1, I can also multiply by 1 over x. You can also multiply by the reciprocal. When you multiply by the reciprocal, x on the top and x on the bottom cancel, and you're left with multiplying that x. And if you notice, I end up with the exact same thing as if you use the hamburger method. So really, it's whatever makes your heart happy. I like to use the hamburger method, but do you. Do whatever makes you happy. Okay. So I'm going to go ahead and get rid of all of this. Now that I finally have simplified my expression, I'm almost done. This is what I'm left with. And before I begin to try to evaluate the limit, is there anything else that I can simplify? Yes, there is. I have an x on the top and I have an x on the bottom. And the reason why I can do this is because this x on the outside of the parentheses is not bound by addition. The addition is in the parentheses. It is being multiplied. So because it's being multiplied, I am able to simplify it out from the top and the bottom. So once I do that, now my final expression, and I'm ready to evaluate my limit, is going to be of 4 plus 2x. And remember, that is in the denominator, so it needs to stay in the denominator. And I can put that numerator of 1. Now I am ready to do direct substitution. So if I plug in 0 into x, I'm going to get that the limit as x approaches 0 of this function is going to be 1 over 4 plus 2 times 0, which is just 1 over 4. So my limit, and I don't know if you guys have noticed, and I'm pretty sure I mentioned it in another video, that you can never just write your final answer and box it in. It needs to be equal to the limit of the function that you're trying to find the limit for. So your answer needs to be a complete answer. It just can't be a numerical value. And same thing, I do have a removable discontinuity. Removable discontinuity at my x that we were approaching is 0, and the limit value was 1/4. Okay? So extremely similar to the last problems we just did. Instead of factoring, I'm using complex fractions to avoid undefined values. Okay, I'm going to do one more with you, and then you're going to do one on your own. So exact same thing here. I can't plug it in directly. I can't use direct substitution because I'm going to get undefined in the denominator, and there's no factoring. And I can see that I have two fractions that can be combined together. So I'm going to start by getting them to have the same denominator by multiplying by each other's denominators on the top and on the bottom. All right. Now I can simplify a little bit. I'm going to get x plus 3 over 3x plus 3 minus 3x plus 3. And now that I have the same denominators, you can distribute the denominator if you want to. You don't have to. I'm not going to. And my expression here is x, 3x plus 3. Okay. Once I combine these denominators, again, remember, everything I just did was only the numerator. I still need to take into consideration my denominator. And in this case, my denominator is x. So just be really careful you don't forget about your denominator. That's another huge mistake that I see students do. They'll do all this work to combine the fractions in the numerator, and then they forget that the denominator exists. Okay, so I just brought down my denominator of x, okay, and I put it over 1 so that we can have a fraction over a fraction situation. And so again, you can either hamburger method or multiply by the reciprocal. I'm going to do the hamburger method. And so my new numerator is going to be x, and my denominator is going to be x, well, 3x, x plus 3. And again, because I have an x on the outside that is not bound by addition, it's being multiplied, I am able to simplify the x on the top and the bottom. And so that leaves me as a final expression 3x plus 3 on the denominator. Be really careful. Whatever is in the denominator, keep it in the denominator. You can't rewrite stuff. So now I'm ready to evaluate my limit, and I'm doing this as x approaches 0. And my final expression here was 3x plus 3. Once I plug in 0, I'm going to get 1 over 3, 0 plus 3. I'm going to get 1 over 9. Okay? And again, remember, all of our final answers always have to have the entire limit written out. I like to use the function already simplified. You could use the original function, up to you. And removable discontinuity at, I was evaluating x as it approached 0, and my limit value is 1/9. Okay, you're doing the next one on your own. So pause the video, really challenge yourself. Copying the notes all the time isn't going to help you master the content. You really got to challenge yourself. Pause the video. And if you get stuck, you can always press play. I'm going to resume with the solution. Okay, I am back. This is a solution for example number 3. This one was a little bit different because the denominator was the complex fractions that you had to combine together. So I try to get them to have the same denominator here. And so once I did all this math, my final denominator was negative x over 4x plus 4. And so I applied that here as my denominator, and I brought over the x as my numerator. Okay. And I did the hamburger method, and then there's my limit and my removable discontinuity. We're going to go ahead and move on. And so again, on this theme of evaluating limits algebraically, sometimes factoring will work, sometimes complex fractions will work, other times you don't have a complex fraction and you can't factor. In this example, I have a fraction, but it's not a complex fraction. This is just a regular fraction, numerator and denominator. And so I'm given a couple hints here in the directions. It says multiplying numerator and denominator by the conjugate. So if you recall from Algebra 2, a conjugate looks like a binomial. So two values that can be added together, right? The conjugate would be those exact same values, but instead of addition, it's subtraction and vice versa. Now, why is the conjugate used? The conjugate can be used to rationalize an expression. It can be used to make an expression real numbers. In this case, I have the imaginary variable, imaginary number of I. And if I were to take a plus bi and multiply a minus bi, and I use the box method or FOIL to multiply here, I end up with, instead of imaginary numbers, I know that I squared is the same as -1. I end up with an expression that is not imaginary, that does not have any i's. So the conjugate is useful when we are dealing with an expression that has either a radical or an imaginary number that we kind of want to get rid of. So for this example, I'm going to use the conjugate because right now, if I use direct substitution and I plug in 0 into my denominator, this is automatically undefined. So the conjugate of the numerator, I have two values that are being subtracted. I have this value minus this value, so two values. And I'm going to take those exact same values, and instead of subtracting them, I'm going to be adding them. So my first value is the square root of x plus 1. The second value is 1. And instead of subtraction, I'm going to be using addition between them. And if whatever I multiply, I can't just introduce an expression and multiply it. I'm changing the math problem there. So I would need to do it also to the denominator so that it doesn't change the math problem. Okay. So now I have a binomial multiplied with another binomial in the numerator. Okay. And again, just to recall, in case you forgot, a binomial is anything where you're adding or subtracting two terms. So 1, 2 terms, that's one binomial. 1, 2, 2 terms. Okay, so that's why I'm saying I have two binomials and they are being multiplied together. How do we multiply binomials? Well, I just said it earlier. When I multiply binomials, you can either FOIL or use the box method. If you are used to using the box method, there's nothing wrong with it. However, I do think that you need to become familiar with FOIL because it's so much more efficient, it's faster, and remember that the AP Calculus test is timed. So anywhere you can save time, I recommend doing it. So I'm going to FOIL this, but you could box method if you want to. FOIL stands for first, outer, inner, and last. So if I multiply these two expressions that are first in the parentheses, I'm going to get radical x plus 1 times radical x plus 1. So that is being squared. The outer values, what is on the outside of the two parentheses? I have radical x plus 1 times 1. So that's just going to be radical x plus 1. What is on the inside of my parentheses? I stands for inside. So the inside of the parentheses, it's going to be -1 times radical x plus 1. And last, what is last in the parentheses? -1 times 1. Okay. Again, I don't like to waste time using the box method, but if you're like, how would I get that using the box method? This is the one and only time. I'm going to show you guys. So you would do your x plus 1 minus 1, and then you do your radical x plus 1 plus 1, and then you multiply rows and columns. Okay, you should get the exact same expression that I got. Okay, so now that we have FOILed this, let's see what's going to cancel. Usually these two terms cancel whenever we deal with the conjugate, and so I'm left with radical x plus 1 squared. However, if you remember, a square and a square root are inverses of each other and they cancel, right? So I'm left with x plus 1 from here and then minus 1. Okay, so x plus 1 minus 1 is just equal to x. So after all of this multiplication of my numerator, after FOILing this out, this all comes down to just equal to x. Okay, so this is my numerator. Now let's do the denominator because we haven't done the denominator. And so if I combine what I got for the numerator and I attach my denominator, and again, this is where my denominator is coming from. Let me remind you guys. here is my denominator, and I just brought it down. And the x was from my numerator. Okay, hopefully the color coding is helping a little bit. And so before I move on, I'm noticing that something is the same on the top and the bottom. X on top and x on bottom. This x is not bound by addition. It's being multiplied with that expression, which is why I can cancel. Okay. And so once I simplify out that x, I'm left with 1 over radical x plus 1 plus 1. And this is my final expression. I've done the numerator, I did the denominator, and now I can evaluate my limit. So evaluating my limit, I get the limit as x approaches 0 of 1 over radical x plus 1 plus 1. I can do direct substitution. I'm going to get the square root of 0 plus 1 is radical 1 plus 1, which is 1 plus 1, which is 1/2. And so finally here, the limit as x approaches 0 of my function equals 1/2. And I know that there is a removable discontinuity at x was approaching 0 and my limit value is 1/2. Ta-da! I'm doing one more and then you're going to do the last one. Okay. So same thing here. I can't factor. I can't use direct substitution because if I plug in 4 in here, I'm going to get 4 plus 5 is 9, and the square root of 9 is 3, and 3 minus 3 is 0. That's undefined. So I'm going to use this idea of the conjugate once more. And instead of the conjugate being used in the numerator, I'm going to use the conjugate in the denominator because of that radical. So I'm going to be multiplying by radical x plus 5 plus 3. Instead of the minus 3, it's going to become plus 3. And I'm also multiplying that on top. Okay, now I'm ready. So in the numerator, I'm going to have x minus 4 and radical x plus 5 plus 3. That's my numerator. The denominator is going to be radical x plus 5 minus 3 times radical x plus 5 plus 3. Okay, I'm going to use FOIL in the denominator. Okay, again, you can use box method if you want. I'm going to FOIL. So first values are the radical x plus 5s. I multiply them times each other, so they become squared. On the outsides, I have 3 radical x plus 5. On the inside, I have minus 3 radical x plus 5. And last, I have negative 3 and 3. So that's going to multiply and give me negative 9. Again, I know I'm like a broken record, but if you don't know how to FOIL, you should YouTube it and learn how to FOIL before school starts. Okay, so plus radical x plus 5, the plus 3 radical x plus 5, and the minus 3 radical x plus 5 are going to give me 0. And I also know that the square and square root go away. They're inverses of each other. So I'm left with x plus 5 minus 9. X plus 5 minus 9 is the same thing as x minus 4. Okay, so what is x minus 4? Remember, I was foiling the denominator. So x minus 4 is my new denominator. Okay, so instead of all this crazy stuff in the denominator, it just becomes x minus 4. Okay, and so now let's bring over the numerator. I thought we were going to have to multiply the numerator binomials, but I don't even have to because check it out. X minus 4 on the top, x minus 4 on the bottom. It's bound by multiplication, so I can do that on the outside of those parentheses. And so I'm left with my final expression before I can evaluate my limit is x plus 5 plus 3. And now I'm ready to do this limit. So I'm going to say the limit as x approaches 4 of radical x plus 5 plus 3 is going to give me, well, let's see, if I plug in 4, I get radical 9 plus 3, which is just 3 plus 3, which is 6. Okay. So let me see if I can scoot down a little bit and make some space here. I'm going to say that the limit as x approaches 4 of radical x plus 5 plus 3 equals 6. Final answer. And then remember, my removable discontinuity is happening at x was approaching 4 and my limit value is 6. Ta-da! Okay? Go ahead and pause the video and try the next one on your own. Alrighty, everyone. Feel free to pause, compare your work, check your work. I multiplied by the conjugate of radical x plus 1 plus 2. And then I FOILed the numerator. And here is my work of foiling the numerator. My numerator became x minus 3, so I plugged it into here as my new numerator. And then the x minus 3 simplified out. I was left with 1 over radical x plus 1 plus 2. And then I used direct substitution to evaluate my limit as x approaches 3. My final answer for the limit was 1/4, which makes my removable discontinuity at 3, 1/4. All right, thank you, everyone.